welcome to my presentation. I have, sorry, I have to see how I can switch to the next slide. Yeah, now it works. Okay. So I put my presentation in 3 parts. One is introduction to high frequency oscillation. The second one is about high frequency with volume guarantee. And the third one is about the benefits of volume guarantee and high frequency oscillation. So let's start with a few words about the basic introduction. And you know this kind of statements, and this is still valid today. So respiratory failure due to lung injury is a major cause of mortality in preterm infants, and in extreme premature infants weighing 500 to 750 gram IVH occurs in about 45% of neonates. And there are many other of these questions. So our goals definitely must be to ensure lung and brain protective ventilation if we give respiratory support. Clinical strategies, there are many, but I think one is important: to achieve stable blood gases, stabilize and recruit the alveoli, and reduce the strain and stress in the lung. So if we look now and compare conventional ventilation to high frequency oscillation, it's important to understand that the pressure transmission to the alveoli is totally different. And you can see in the slide, you can see on the right side, you see the conventional ventilation from the airway opening, means the ET tube connector, down in the to the upper airways and down to the alveoli. And you see in conventional ventilation, the pressure we see in the patient circuit and airway opening is really applied and is given to the alveoli. During high frequency oscillation, we all know that we have high amplitude at the airway opening, but the alveoli will see only a little bit of these oscillations. And the reason for this is simply that we have a big dampening of this amplitude. So let's have a look to the basic settings of high frequency oscillation. So it's basically, the first is that we have a mean airway pressure, which is the, let's say, average pressure on which the oscillations are happening. Then we have the amplitude of the oscillations, which will deliver basically an oscillatory tidal volume. Then we have the frequency, and we heard already a few remarks from Professor Sam about when to use what frequencies. Ideally, there's not one specific frequency for a specific disease, but there's a certain range, and there are differences when to use what frequencies. Then we have the inspiratory to expiratory ratio. Classically, it was used mainly and is today used mainly 1:2 inspiratory expiratory ratio. However, there are also publications, for example, from Jane Pillow about I/E ratio and the impact to the mean airway pressure in the lung. So not what we see from outside, what is displayed on the ventilator screen, but what is really happening in the lung. And there we see that with an I/E ratio of 1:1, really the mean airway pressure in the lung is equal to the pressure what we see at the airway opening. However, the more I go to 1:2 or 1:3, the intended see the mean airway pressure in the lung will be below of that what we see in the airway at the airway opening. And then finally we have the oxygen concentration. If we look at the oxygenation control, there are basically 2 parameters to set and to influence this, and this is FiO2 and mean airway pressure. If we look to the mean airway pressure, and Professor Sam spoke already about this, about the importance when and how to and what to use for the mean airway pressure, and surely it's basically important to adjust the right mean airway pressure to optimize the lung volume and the alveolar surface for the gas exchange. It's important in certain diseases to recruit atelectatic alveoli, but we have to be careful that in some diseases recruitment is not possible, and therefore also, let's say, recruitment maneuvers might be not helpful. Furthermore, the mean airway pressure surely prevents the alveoli from collapsing, so from de-recruitment, and it surely in the right way, if the mean airway pressure is adjusted properly, then it avoids as well over distension. We come later back to this point. If we look now to the management of CO2 removal, we all know that the main parameter of CO2 removal is the oscillatory amplitude. Important is that if you look to the oscillatory amplitude, that this amplitude is strongly influenced by different factors. And Professor Sam mentioned already that, for example, the patient circuit is an important parameter. Therefore, it's important to use a non-compliant or low-compliant patient circuit if we give high-frequency oscillation. Then surely also the water level in the humidifying chamber is important, because also water can't be compressed, but air in the humidifying chamber can be compressed, and therefore this air in the humidifying chamber is a compressible volume and therefore increasing the compliance of the patient circuit. So it's good to use maximum water level, a small humidifying chamber, and a low compliant patient circuit. But however, as well, factors like frequency or I2E ratio are important to the maximum achievable oscillatory amplitude, because it's simply the fact that a lower frequency and a longer inspiratory time in total will give the ventilator more time to build up pressure. The oscillatory amplitude is causing an oscillatory tidal volume. And also the tidal volume surely is again influenced by certain factors. And I mentioned already the frequency and the I2E ratio, but the main parameter of oscillatory tidal volume is surely the ET tube diameter, because high frequency oscillation is not so much dependent, the tidal volume is not so much dependent on the compliance of the lung, but it's very sensitive depending on the resistance of the airways and the ET tube. So keep this in mind, because if you have, for example, mucus accumulation, you will see that the tidal volume can drop very quickly. Okay, and the oscillatory tidal volume surely is the main factor for removing CO2. This is the same like in conventional ventilation. If we now speak about CO2 removal, we have to recognize that the dependencies on tidal volume and frequency is different compared to conventional ventilation. I put here the graphics. You see in the graphic the PaCO2, and on the x-axis we see the minute volume for conventional ventilation. It's tidal volume times the rate. Yeah, this is for conventional ventilation. So we know the higher our minute volume, the lower the PaCO2. But in high frequency oscillation, it's not simply the minute volume, it's the dCO2, the dissociation coefficient for CO2. And this is calculated like VT high frequency to the power of 2 times frequency. So you see that the tidal volume in high frequency oscillation has a bigger impact than the frequency. We come back to this later today. So I put it here again. The dCO2 is tidal volume to the power of 2 times frequency. And here, this formula is very important to remind because small changes in tidal volume can influence a lot, or can influence a lot the CO2 removal capabilities of high frequency oscillation. So we see as well in this picture, oscillatory volume and frequency both are influencing the gas transport coefficient, the dCO2, and this basically is influencing the PaCO2. how to improve CO2 removal. So first increase the amplitude if you have not enough CO2 removal capability, then review the resulting tidal volume. And if this does not improve CO2 removal, then only consider the decrease in frequency. And you would immediately say, why decreasing frequency? Because frequency is as well in the formula of dCO2. Yes, but the frequency, if I reduce the frequency, I give the ventilator much more time to deliver tidal volume. So as the tidal volume in this case then goes up, but the tidal volume is in the formula to the power of 2, therefore it overcompensates then the loss of frequency and the dCO2 will increase. That's the reason why sometimes if you can't increase the oscillatory tidal volume more, a reduction in frequency makes sense. Let me come now to volume guarantee. You see here a comparison of the conventional volume guarantee and high frequency oscillatory volume guarantee. On the left side, we see a volume guarantee during conventional ventilation. You see that a tidal volume is measured during an expiration, and then the ventilator decides for the next breath what pressure is the right one. So if necessary, it increases or decreases the pressure of the next breath. And this happens continuously, so the pressure is automatically readjusted to meet the set tidal volume. In high frequency oscillation on the right side, this is very similar. The ventilator again is measuring the high frequency tidal volume, and is then, according to your set target high frequency tidal volume, is automatically adjusting the amplitude of high frequency oscillation. So how does this look like? We will see this later in a live demonstration as well, but high frequency volume guarantee can compensate for changes in resistance and compliance. And this is of the lungs and surely as well of the circuit. High frequency volume guarantee can stabilize the ventilation and blood gases and has the potential to prevent uncontrolled hyperventilation and to reduce, due to this, the risk of periventricular leukomalacia. And we have heard this already. We have to be careful in high frequency oscillation with its capability to remove CO2 from the blood. And there's one statement which was from a Swiss newspaper here. This was even in 1999. There it was says one of the problems with high frequency oscillation is that it is as it is so effective at eliminating CO2, it is very easy to produce severe hypocapnia. I would like to come for a minute to lung recruitment. And we all have seen these pictures, what you see here on this slide. You see here from the left in the upper line, you see the inflation of I think this is a rat lung. So you have to build up here the pressure. You see below here, you see the pressure, what is applied. So it started from 0, then to 4, to 8, to 12, to 16, to 20 millibars. And you see that the lung needs some time until really the opening pressure is reached and the lung is fully inflated. So if then the pressure is reduced stepwise, you see that the lung will not deflate immediately. It will stay inflated for a longer time, even here until 8 millibars, yeah? And only below 8 millibars, you will see some deflation of the lung. So, and that reminds us in the hysteresis of the lung. And so where we should, and we should make use out of that, and therefore we should high frequency oscillate on the expiratory limb of this passive PV loop of the lung. This is well demonstrated and how to go there and how to recruit a lung during high frequency oscillation, give possibly surfactant, then re-recruit the lung and find the optimal distending pressure. This is an illustration which is based on a publication from Dräger. from the year 2006. And here it's well described what is done. And you see this in the pictures on the right side. So first you try to open the lung and try to reach really the opening pressure so that the lung is fully inflated. As soon as you have done this, you would reduce the mean airway pressure stepwise until you come to a point where you see that the closing pressure is reached, means that the first alveolar units are collapsing. If you detect this, then you go back to the opening pressure and then stay to about 2 millibars above the closing pressure. So this is the idea of recruitment of a recruitable lung. However, why I'm explaining this is that if you do this kind of recruitment maneuver, as the lung is opening slowly, you would see immediately that your tidal volume also goes up. And with this increased tidal volume, what is visible here on the right side, also your PaCO2 will drop dramatically over a short time. And so in this respect, during such a recruitment maneuver, volume guarantee can be of help, because volume guarantee would continuously readjust the amplitude to stay with the set tidal volume. So volume guarantee can be as well very helpful in while doing recruitment maneuvers during high frequency oscillation. So benefits and outview. There are a few publications out there about volume guarantee in high frequency oscillation. The first one I would like to show you is from ISCAN. This is the impact of volume guarantee on high frequency oscillatory ventilation in preterm infant, a randomized crossover clinical trial. And what they have done is they simply compared high frequency without volume guarantee. You see this here in the bars on the left side. High frequency without volume guarantee compared with high frequency with volume guarantee, and they simply measured the time when the tidal volume was really in the target range. And you surely see that volume guarantee is working. In fact, we see that 80% this is in the target volume. But as well, we see that the DCO2 consequently is also closer at the target range. But we see surely the amplitude consequently is more fluctuating because this is continuously readjusted by the ventilator during high frequency oscillation. A study from Chen, which was published in 2019, had then this conclusion. In this study, the preterm infants with HRF ventilated using HFOV combined with volume guarantee had a reduced combined outcome of death or BPD and hypercarbia compared to with those who received high frequency oscillation alone. The third one I want to show you is from Enomoto, and this is only a pilot study, so not many patients were involved here, but he as well found out that high frequency combined with volume guarantee attenuates fluctuations of SpO2 and PaCO2, which prevents hypoxia and hypercapnia, and thus might result in a more favorable prognosis. However, this is a relatively small study. I want as well to mention one bigger, really relatively big study, what was, let's say, initiated by Dräger directly in the United States. And you might know that high frequency oscillation in the US needs a special approval from the FDA, which is called the pre-market approval. And that means we first have to show safety and effectiveness in a well-controlled study. And so we have done this study. In the meantime, the patient involvement is stopped or is finished, yeah. And we have involved 225 patients in the study. However, we until today, we have not the results, but all of these patients were ventilated with volume guarantee in high frequency oscillation. So it will be very interesting to see the study results, and we expect the results beginning of next year. So this will be definitely a big study using volume guarantee in high frequency oscillation. My last slide is only about a recommendation. We have produced a small booklet with Jane Pillow from Melbourne and from Perth, sorry. Yeah, this is about high frequency oscillation theory and practical applications. If you're interested in this booklet, please contact your local Dräger sales representative, and we will be happy to provide a booklet of this, or you can download this at the Dräger web pages.
Yes.
Hello and welcome to our demonstration parts of this webinar. As we are running a little bit out of time, I will keep it as short as possible. However, for Singapore, this webinar is a kind of launch of our new baby log, and therefore we would like to show you a little bit of that and demonstrate the use of volume guarantee during high frequency oscillation. So before I start, you see on the right, to my right, you see the new baby log VN800. And I will use this for my demonstration. Furthermore, I would like to explain you a little bit about the setup here. So you can see here, Michael, can you check? Okay. You see here that we are using a test lung with 2 bellows within a T-tube. We have connected this to a low compliant patient circuit here, which nevertheless is very flexible, but it has a low compliance, which is important for the power of high frequency oscillation. Then we see here a low compliant humidifying chamber to optimize our output of the ventilator. Okay, then let us now come to the high frequency oscillation. What you see here, the device is running in pressure controlled SIMV. We see here on the screen, we see the pressure waveform, the flow waveform. We see the FI2 P box, the mean airway pressure, the minute volume, and the respiration rate. So what we now will do, in the first step, we want to switch now to high frequency oscillation. So we pressed here the button for high frequency oscillation. Now you will see the pre-settings of settings for high frequency oscillation. We can now pre-adjust parameters like, for example, the frequency here, but we stay here for the moment at 10 Hertz as a starting point. And we confirm this selection of the mode by the rotary knob. And immediately you see that the ventilator starts with the high frequency oscillation. What we see now here in the top is again pressure below the flow waveform. To adapt our screen here to high frequency oscillation, I will change the view here to the view 2, where we have created an optimized view for high frequency oscillation. You see now pressure and flow wave, and you see below of this, you see the trend for the DCO2, for our CO2 removal surrogate, so to say. Currently, we see an FI2 of 21%. Sure, this is a test line. We do not need to increase this. Mean airway pressure is currently running at 10. So before we had a mean airway pressure in conventional of 8.2. So this is a little high. Usually, as we are working with one-to-one, we would in the first step stay close to the mean airway pressure what we have in conventional ventilation. With 1-to-2, we would increase this a little because we have lower mean airway pressures in the lung. So I would adjust this now, the mean airway pressure, to 8.5. We are at 1-to-1. We stay for the moment in 1-to-1, and we have an amplitude of 21 millibars. which delivers, and you can see this here on the screen on the right side, which delivers currently a tidal volume of 2.9 milliliters. We are simulating currently a patient here of 1.5 kilograms, so a relatively big patient. If we calculate roughly 2 milliliters per kilogram body weight, our initial target could be around 3 milliliters. So we are quite fine with the 2.9 milliliters. We could increase this a little bit by using the amplitude setting and increase this a little bit. So then we finally are at 3 milliliters per kilogram. So, but now patient's compliance is improving, and I will simulate this now and will say, okay, compliance is improving. Now we see that the tidal volume at the same amplitude is increasing to 3.5, 3.6 milliliters. What we now see immediately, also a little bit delayed, but what is as well happening, that is the dCO2 is climbing up. We all remember dCO2 was tidal volume to the power of 2 times frequency. We haven't changed the frequency, but tidal volume went up. Tidal volume went up only by 0.5 milliliters. Yeah? However, the dCO2 was increasing now roughly by 25%. That shows that we are now the potential for CO2 removal was increased by 25%. So therefore, we see very clearly only small tidal volume changes are influencing already a lot the CO2 removal capabilities of the ventilation. Okay, what you normally would do now is you would touch here your amplitude setting and would reduce your amplitude to come back to the 3 milliliters, what we have seen before. However, I would like to show you here volume guarantee. And so how to get to volume guarantee, you first press the small knob here to the right with the 3 dots. And if we open this, then we find here volume guarantee as one of the stapulators. So we are now here with the volume guarantee settings. You can see that we can set the tidal volume. It was still remembering the previous settings, and this was 3 milliliters. This is okay for us. Then we can adjust the maximum allowed amplitude setting, and we, in the first step, we stay with the 30 millibars amplitude, and then we switch the whole thing on. We need to confirm this switching on this, and then we close this dialog. Now we see that the tidal volume is now automatically reduced here, and we see as well that the pressure was needed, the amplitude is as well was reduced from 22 to 17 now, and we end up now with the 3 milliliters what we set as a target for the tidal volume. So let's imagine now we initiated high frequency oscillation, and now we have the accumulation of mucus in the airways, and so I will now simulate this, and so the resistance is now increasing, and so I will try to simulate this currently a little, and you see it now here, what is happening. Yeah, so we see that currently we are in the meantime at the 29 millibars, 28 millibars, so much bigger amplitude, but the tidal volume now stays at the 3 milliliters. Yeah, so it's automatically reacting to this situation. However, if the mucus accumulation gets bigger, and this I simulate now, then your tidal volume will drop even more. And what we will see now, you see that the delta P is not increasing anymore because we have limited the maximum allowed pressure to 30. Now the tidal volume dropped to 1.6, and what the ventilator is currently issuing is a tidal volume low alarm. So it says VTHF not reached. So now it's up to you to look for the patient and find out what was causing this increase in amplitude to 30. In this case, possibly you would suction the patient and would therefore increase the resistance again to bring this down. And so then the ventilator would be able to do this. But it could be as well that you look for the patient, but you realize that you have to allow the ventilator more, let's say, more amplitude. And if you want to allow this ventilator more amplitude, you simply can touch here the maximum amplitude and increase this, in this example, up to 49. Yeah. And then the ventilator surely will increase now the P, and in this case I changed as well the resistance a little bit back, and now we see that currently it's used 34 millibar amplitude, and to reach the high frequency tidal volume of 3 milliliters again. So we see this is an automatic regulation what the ventilator is doing during volume guarantee. Yes, and so this is what I wanted to show you. So this is a very short introduction. If you like to get more information, surely contact your local sales representative in your country, and we will be happy to show you more about this ventilator, about the new ventilator, and about high frequency with volume guarantee. So with this, I would like to pass this back to Dr. Sam or Dr. Chopin. I think we will now have a question and answer session, right?
Yeah. Thank you, Thomas, for giving us an overview and a simulated demonstration of HFOV-VG on our new ventilator Babylock VN800. If you have any questions or like to know more about our new Babylock ventilator, please contact our local sales representatives. We have now come to the Q&A session. If you have any questions, please type into the question box in the menu bar. In interest of time, we'll compile all Q&A and share with you who has entered it today. We apologize if we have missed any questions or are not able to answer all questions here. However, since Thomas is doing a live demo for us, can we have two questions for Thomas? First question, is spontaneous breathing of the patient disturbing the HFO with VG?
So can you repeat the question again, please?
Okay. First question, is spontaneous breathing of the patient disturbing the HFO with VG?
Okay, so this is about spontaneous breathing. Let's say you will see, and this is, I mean, usually you see spontaneous breathing and high frequency oscillation. This is not a problem for volume guarantee, as volume guarantee is slowly adjusting the amplitude. So it's not, will not do this from oscillation to oscillation, but it will do this more slowly. So if we have to see spontaneous breathing, this nevertheless, the tidal volume will oscillate a little bit around the target, but it will pretty much stay at tidal volume.
You are not showing the live stream.
Sorry?
We cannot see your screen.
Yeah, we can see your screen.
Yes, we see now.
Okay, thanks.
Sorry. Okay, so this was the question I can ask for. Show this here in the ventilator. I can use the test lung and simulate a little bit of spontaneous breathing, and then you can see this on screen.
Stop now.
Yeah.
You must change something to
Yeah.
the right screen.
So here you see. Currently, I'm breathing here with the test lung spontaneously. You see that you see this breathing in the flow curve, and you see that the tidal volume, the HF tidal volume, is fluctuating a little bit. It's 2.9, 3.1 around this, but it still stays very close to the set tidal volume of 3 milliliters. Okay. I hope I could answer the question properly.
Yeah, thank you, Thomas. Now we have the second question for you. How big is the impact of frequency reduction on tidal volume during HFO?
Yeah, that's a very good question. This is not a little bit. It's quite impressive. To show you this, I can show this here in the ventilator. But to show this, I first need to switch back from volume guarantee, switch off volume guarantee, because what we have learned by Dr. Krüger today is that if I would reduce the frequency here in this setup, yeah, and I can do this here, I would reduce it from 10 to 9, yeah, but nothing will happen. I mean, the tidal volume, you see it goes up a little bit for a short time, yeah, but then it's regulated back to the 3 milliliters, what we have set. So there's no impact to that. So, but however, if I switch off now volume guarantee, I will do this here now. So I switch off volume guarantee. Now I'm back to the previous settings of 22 milliliters, of 22 amplitude. And I have now a tidal volume of 2.6 milliliters. Yeah? If I now go down one more, we are now at 9 hertz. Yeah? If I go down from 9 to 8, compare, now we are at 2.6 milliliters. And if I go to 8, I go from 2.6 to 3 milliliters. So this is 1 hertz, but it's giving us 0.4 milliliters more of tidal volume. So, so this is quite a big impact. But please remember, this impact you will see only if you're not using volume guarantee. If you're using volume guarantee, yeah, then you have to adjust first the tidal volume, yeah, and increase this, because frequency reduction will have no effect to the delivered tidal volume during volume guarantee.